Hi, everyone. Today, what I want to do is just go over some information regarding the AP exam and just some things that you'll find in your packets, okay, that you picked up at the school. So, one of the very first things you see on cardstock in your packet is a bunch of pages, and it's just all the information that you need to know for the AP exam, especially for the free response. So it's like your derivative rules. Um, the different definitions for the derivative at a point, these two different versions, okay? I'm just gonna quickly go through this, all right? Here's all the important tests. I'm gonna zoom out a little bit. I can't, all right. So tests for increasing, decreasing, concavity, closed interval test, first derivative test, second derivative test, concavity test. You can look at all these yourself, okay? If you're given the graph of the derivative, I think this is going to be really important this year because this is interpreting what all of the calculus means, okay? So I would really take a look at this, okay? Two important theorems, the intermediate value theorem and the mean value theorem. L'Hopital's rules down at the bottom. Turning to the next page, you have your integral formulas, integration by parts. Remember to use Lippitt. Fundamental theorem of calculus part 1, part 2, average rate of change of a function, average value of a function, net change or net area, and then total area. Two different ways of, different versions of area. Particle motion formulas, okay? All of that you need to know. I'm thinking they usually ask a particle motion problem on both the A, B, and BC test. And so I'm thinking they're going to ask you more of an A-B question because of some of the things that they're cutting out of the exam this year, okay? And then some more, how do you know when the particle is speeding up, slowing down, moving away from the origin, moving towards the origin? I think they're going to ask you questions like this that you just can't look up in a textbook or Google really fast, okay? All right, and then you have Euler's method. This should be a dot, 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 not an M, okay? Volume of a solid, I think they're gonna ask you this, okay? They're gonna ask you to use either the washer method or the disk method, or if you know the cross-section area, okay? Arc length, the different forms for arc length, if it's a function of y or a function of x. In other words, if you're going vertical or if you're going horizontal. Okay, and then here they are definitely going to ask you something regarding Taylor series, convergence, and all of that, because that's a really big part of BC calculus. That's really one of the main things that makes it different than AB. Okay, so know your Taylor series, how to generate them. We're going to do a lot of review with this through multiple choice and the free response. You'll see in a minute. Okay. Here's the Maclaurin series for 1 over 1 minus x, e to the x, sine x, and cosine x. Those are the four you usually have to have just know. But you're going to have this available to you because it's open note, open book, open internet. All right. For the AP exam, you have everything available. The only thing is if you're trying to search for everything, you're going to run out of time. Okay. So you just have to know this stuff. Okay. So I would still, even though like you don't have to have it memorized, or know these pretty well. I mean, you maybe just during the exam you could use this as a quick reference just to make sure on something, but if you're looking everything up, you're going to run out of time on the exam. Okay. Taylor's theorem with remainder, remainder estimation theorem, or Lagrange error bound, and then you have the alternating series error bound. Okay, and then here's all your convergence tests. Okay, and I cannot zoom out. Sorry, guys. Let me move this slowly so you don't get dizzy. All right. So here's all the different convergence tests, okay, that you should know. All right. And I don't know if I included this sheet or not. I can't remember. This is not going to be on the exam, okay? So this is the part of the class that they've cut out of the exam. We're going to do this after May 12th, okay? So after you've taken the exam, we're going to go back and actually do this last unit on parametric functions and polar functions, okay? So you're not going to need to know this at all for the AP exam, okay? All right, so don't worry about it because we have not covered it, and I purposely didn't cover it because I knew it wasn't going to be on the exam, okay? All right, so there's that part of it that's in your packet. Another thing in your packet is this. And this is a free response, how often they ask the different types of free response questions, okay? And you're gonna have, there's another packet of information that I'm gonna go over in just a minute too. But look at this. Okay, so these are the type of free response questions that they normally ask. Okay, so all of these above the gray is AB stuff. Okay, everything below is BC. Okay, so you're going to be we're going to go over, this is what I plan on doing, is going over the rate and accumulation, particle moving on the line, interpreting graphs, all of these, and you can see how often it's been asked. Okay, now I want to take a couple things off here, okay, because these are the things that this is from a normal AP exam, all right, not this year's. Okay, so they've taken some things off. So what I want you to do is just go ahead and cross this out, because you're not going to have any questions that deal with parametric or vector questions, and you're not going to have anything that deals with polar equations. So see what I'm saying is the only thing that's left is sequence and series. So they're going to ask you that because they want to know that you know the BC stuff, okay? So they are definitely going to ask you this. And look, it's on every single exam, every single year. So we're going to spend a whole week just going over all of, maybe not all of these, but a lot of these different types of problems, okay? All right. Okay. So I think let's look at another packet, and it's this one where it's free response type problems. Okay, and then this just goes through all the different types of free response questions there are, with the exception of one. You know what? I should bring that back. Okay, this one, this is called. I'm calling this function questions, and this is where they give you a function. They want you to find the derivative, or integrate it, or tangent line equation, and they give you the straight out function. Okay, that's what I'm calling function questions. That's a name that I've come up with. This is more of the formal names. Okay, so you have differential equations, and this is just, you can read this. Okay, this is what you should be able to do to answer these questions. Okay, so you have differential equations, and then you have interpreting graphs. I think this is going to be an important part of the AP exam this year, because it's not just like you can look it up and find a rule for it. Okay, particle moving on the line. Those vector and parametric equations they cut out usually deal with some type of particle moving in a plane instead of on a line. And I'm pretty confident they're going to ask the BC students to do this type of problem this year. Okay, you're going to have table questions where you just get your information from tables. Okay. You have rate and accumulation and area volume. And then here's some occasional questions, the implicit differentiation and related rates. And then here's, for you guys, you have these BC topics. Okay, so here's parametric and vector questions, right? They are not going to ask you this year, okay? Because this is the unit that they've cut out of the exam. And same thing with this one, the polar, okay? So this is just a packet I give out every year to my BC students and my AB, but I don't put the BC stuff in there, that I give out to my students so they know what's expected, what they're expected to do, okay? And then this one, they are going to ask you, okay? Definitely they're going to ask you sequences and series. So you can just go through this and just know, okay, this is what they expect me to be able to do on the exam, all right? Okay. So this week, what we're going to work on is we're going to work on differential equations and rate and accumulation problems, okay? And so I'm going to assign a couple free response questions. So what I want you to do, well, that's the introduction, okay, to this. Let's stop there, and then we'll just go, and I'm going to switch over to the free response questions, okay? All right, so what I want you to do is from the 2010 free response packet, turn to question 1, okay? And it's, yeah, just turn to that and just go ahead and pause the video and find that in your packet. Okay, so this is the same question as the AB test. So you're going to see in the video that it's going to say Calculus AB instead of Calculus BC, but it's actually the same question for 2010, question number 1, okay, on the free response. Okay, so what I want you to be able to do is I want you to go through and try to do this yourself, okay? And you can do it a couple different ways. You could do A, B, C, and D, and then go back and watch the video on how to answer them, okay? Or, okay, you can do question or part A, okay, and then watch the video on part A and make the corrections, and then do part B and then do the corrections on part B. So you can do it however way you want, okay? But what I want you to do is try it yourself first and then go to the video, okay? Try to do it that way, all right? Okay, so go ahead and we'll and pause the video and go ahead and start answering these questions on question number 1, okay? So for question 1, there's no snow on Janet's driveway when the snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates on the driveway at a rate modeled by f of t is equal to f times t, e to the cosine t, cubic feet per hour. Okay, so notice this keyword right here, rate, right? So rate modeled by, that's a rate, so which means that's a derivative. And the units are cubic feet per hour. Okay, so if we integrate this, that's going to take away the hour unit, and we're going to be left with cubic feet, which is an amount of snow that's accumulated, okay? So where T is measured in hours since midnight, okay, Janet starts removing snow at 6 a.m., T equals 6. The rate G of T in cubic feet per hour at which Janet removes snow. So this is an in and out problem because they're telling you that it's the rate F of T is the in part and the G of T is the out part. It's the part that's removing snow, okay? Because she's shoveling the snow out, okay? So she's removing the snow, okay? So Janet removes the snow from the driveway at time t hours after midnight is modeled by G of T is equal to this piecewise function. It's 0 for 0 less than or equal to T less than 6. Now, why is that? It's because that's from midnight to 6 a.m. And what do we know? She didn't start until 6 a.m. That's why the rate at which she's removing snow is 0 at that time, okay? And then G of T is equal to 125 for 6 less than or equal to T less than 7. And then it's 108 cubic feet per hour, okay, for 7 less than or equal to T less than or equal to 9. And the very first question is this: how many cubic feet of snow have you accumulated on the driveway by 6 a.m.? So how much has been put onto the driveway, okay? All right, so let's go ahead and do that first one, okay? So I'm gonna write 2010 number 1, and I'm gonna put A here, okay? All right, so how many cubic feet of snow have accumulated on the driveway at 6 a.m.? So that would be an integral, and we'd go from 0 to 6 of our f of t. It's the function that's putting snow onto the driveway, right? And that would be 7t e to the cosine of t and then dt. All right, and so we're going to go to our calculator and we're going to put that into our calculator. So on our calculator, what we want to do is we want to press alpha and then window and then select function integrate, so number 4. Okay, and we want to go from 0 to 6. Whoops, I didn't go up. Okay, 0 to 6. And what I would do is I would go and put my function in for y1, okay? A lot of times it's good to store these in your calculator, all right? All right, so it was 7, and then t, we have to use x instead of t, and then e, right? And then second natural log, okay, e to the cosine of t, or x in this case. Okay, now, all right, one thing we got to make sure on, because this deals with the trig function, we got to make sure we're in radians. So check your calculator, make sure up here at the top says radians, all right? Okay, and now what we can do is go back to our home screen, okay? And right here, instead of having to type that function out, because we may need to use that function for other things, all right, we can type in just y1. So then alpha and then trace, and that's where we get our y variables, right? y1. And then x, because we're integrating with respect to x, and press enter. And there we go. And we went around to 3 decimal places. So 142.275 cubic feet of snow. Okay? All right. Let's go back and put that on. So from our calculator, we know that this integral came out to be 142.275 cubic feet. Now, another way we can write this is feet cubed. That's cubic feet also. So either one of those would be right, okay? All right, and that's the answer for part A. All right, for part B, we want to find the rate of change of the volume of snow on the driveway at 8 a.m. All right, so F of T is the rate at which the snow accumulates on the driveway, right? And G of T is the rate at which the snow is being removed. So how much snow is what's the total amount of snow? What's the rate of change for that? Well, it would just be F of 8, and F of 8 would be the rate of change at 8 a.m. minus, because this is removing, right? So minus G of 8, and that's all we have to do is do F of 8 minus G of 8, okay? So for part B, the rate of change of volume of snow on the driveway at 8 a.m. would simply be F of 8. That's the rate it's being put onto the driveway and at 8 a.m. and then minus what's the rate at which it's being removed. Because if you combine those, you get the rate at which the volume of snow is changing at that moment, okay? All right, so we're gonna need to put this into our calculator, okay? Now, one thing about G of 8 is we know this one is it's gonna be F of 8. We're gonna need to use a calculator to figure that one out, okay? And then minus, and then G of 8, we actually know, because for 7 less than or equal to T less than or equal to 9, okay, we know that it's 108. So F of 8 minus 108. Okay, and so that's going to be about, because we're going to have to round this value, okay? So I'm going to go back to my calculator and put F of 8 in. So since we stored the F function in for y1, we can just plug this into y1, all right? So we're going to press alpha, trace, and then select number 1, y1, at 8, and then minus the 108. And we get negative 59.583 cubic feet per hour, okay? So we'll go back and we'll record this on our paper. So this would be, again, recording it from our calculator, negative 59.583 cubic feet per hour. And that's it for part B. Let's move on to part C. For part C, let H of T represent the total amount of snow in cubic feet that Janet has removed from the driveway. Okay, so we're talking about how much she's removed at time T hours after midnight. Express H as a piecewise defined function with domain 0 less than or equal to T less than or equal to 9. Okay, so G of T is a rate. So, and it represents the rate at which she's removing snow. So if we integrate this, all right, if we integrate G of T, what we're gonna get is the amount of snow. Now, we gotta understand that when we integrate it, it's gonna give us the change, right? So how do we get the amount at a certain time? And we gotta use the fundamental theorem of calculus, okay, to do this, okay? So let's go to our paper and I'll show you how to do that. Okay, so for part C, okay, we know that for 0 less than or equal to t, and we're going to do this all the way to less than or equal to 6, okay, h of t is going to equal, now we're starting at 0, right? So that's going to be h of 0, the starting amount, all right, plus the integral from 0 to t of, now it was g of t, so we got to use a dummy variable because we're using t to say when the time it's going to stop, or the time at which we're trying to find how much snow she's removed, okay? The total amount of snow that she's removed. So this would be g of s and then ds, okay? So for this time interval, we know g of s is 0, okay? So this would be h of 0 plus the integral from 0 to t of 0 ds. Well, this is going to be 0, right? And this is going to be 0. So for this, it's just going to wind up being 0 because our constant 0, all right? So if we pull that constant 0 out, we're multiplying by 0, right? So it's going to come out, this integral is going to come out 0. And we know h of 0 was 0 because when at midnight, she hadn't started removing snow yet, right? So at time 0, there was no snow that she had removed, okay? Now we need to move on to the next time interval, which is 6 to 7. All right, so we're going to look at 6. All right, and we're not going to do less than or equal to, but less than t, less than or equal to 7. Now it becomes this, h of t is equal to, all right, so now we're going to go from 6 to 7, and we want to integrate from 6 to 7, right? So we need to know the starting amount, right? H of t is going to be h of 6, because that's the amount at time 6, and then we're going to add to that the integral from 6 to t, and again, g of s ds. Okay, so h of t, now what is h of 6? Okay, well, we know at 6, it's 0, right? So this is still 0. Plus, and this becomes the integral from 6 to t, and g of s from 6 to 7 was 125. So this is 125 ds, right? Okay, so then this becomes 125 s evaluated from 6 to t. Okay, so that'd be 125 t minus 125 times 6. Well, both these have in common is 125, so we could factor that out. So this would be 125 times t minus 6. Okay, and that makes sense because this doesn't start until hour 6. She doesn't start removing snow until hour 6. Okay, now we need to do one more time interval, right? From 7 to 8, or 7 to 9, not 7 to 8, 7 to 9. Okay, so we've already included 7 here, so it's going to be 7 less than t less than or equal to 9, right? And then our h of t would equal, okay, so we're going to start integrating, and we're going to go from 7 to some value, right? So we got to start out at h of 7 plus the integral from 7 to t of g of s ds, okay? So then that's equal to, okay, so h of 7, actually we can figure out h of 7 because h of 7, we got to put 7 in for t here. So 7 minus 6 is 1. 1 times 125, that's 125. H of 7 is 125. So 125, and then plus, then the integral from 7 to t, and from 7 to 9, our g function is 108. So this would be 108 ds. Okay, so I'm going to wrap back around here. This would be 125. I'm going to slide it up a little bit too. This would be 125 plus, and this would be 108 S, and we want to evaluate that from 7 to T. So this would be 125 plus 108 T. I should put parentheses around this or bracket. 108 T minus 108 times 7. Well, what can we do here? We can factor out 108. So this becomes 125 plus 108 times T minus 7. Okay, so what is this h of t function? Okay, so h of t, this piecewise function, is going to be equal to, and from 0 to 6, it's just 0. So 0, h of t is 0, from 0 less than or equal to t less than or equal to 6. It's going to be the 125 times t minus 6, 125 times t minus 6. But that's going to be from 6 less than t less than or equal to 7. And then it's the 125 plus 108 times t minus 7. So 125 plus 108 times t minus 7. But that's going to be from 7 less than t less than or equal to 9. And we've written a piecewise function for the total amount of snow that Janet has removed from the driveway for any time t. Okay. All right. So that's the answer to part C. Okay. Now let's go on to part D. So for part D, what we want to do is we want to find how many cubic feet of snow are on the driveway at 9 a.m. So to find how many cubic feet, we're going to have to integrate how much has been added, right? That's the f of t function. And then we're going to have to subtract out the amount of snow that's been removed. And this h of t that we figured out in part C, we can use, right? Because that's going to give us the amount of snow that Janet has removed by 9 a.m. Okay. All right. So here we go. Let's go to part D. Okay. So this is 2010, number 1. And this is going to be part D. Okay. All right. So the amount of snow would be given by the integral, and we're doing this at 9 a.m. So it started snowing at midnight, which is 0 to 9, and f of t, right? dt. Now that's going to be how much snow has piled up on the driveway, okay? By 9 a.m., that's going to give us the amount of snow that's on the driveway that's been, well, let me back up. That's the amount of snow that's fallen onto the driveway by 9 a.m., okay? Now, what else has happened is Janet started removing it, right? So we got to remove from this how much she has removed. So minus h of 9, because remember, the h function is the total amount that Janet has removed. Okay, so if we do this calculation, it's going to give us how much snow there is on the driveway at 9 a.m. Okay, so this would be, we're going to do an approximation because we got to put this into our calculator. So we're going to go back to our calculator and put this in, okay? Okay, so we want to integrate. So we want to press alpha window and choose number 4. And we're going to go from 0 to 9. And our f function, which is y1, so alpha trace and then y1. And then dx. Okay, now that's going to give us the accumulation of snow on the driveway, okay, at 9 a.m., okay, up to 9 a.m., how much snow is accumulated. Now what we have to do is we need to remove, okay, whoops, and we want to press minus, okay, and then we want to do h of 9. Now h of 9, if you recall, right, on our paper, it's going to be 125. Whoops, and I need to do a parenthesis because we have to subtract the entire amount. So parenthesis 125 okay, and then plus, and then 108, and it's going to be 9 minus the 7. Okay, and then, okay, so let's just double check on the parentheses. Okay, this is really 2. If you put in 2 right here, you wouldn't be wrong because 9 minus 7 is 2. Okay, and then we'll press enter, and we get 26.335. Okay, and that's how many cubic feet of snow is on the driveway at 9 a.m. Okay, so we'll go back and we'll record this on our paper. And so on our paper, we're going to record 26.335 cubic feet. And we're done with our first rate and accumulation problem. Okay. So go to the 20,000 or 2011, not 20,011, but 2011 free response booklet that's in your packet, and turn to problem number 5. Okay. And it's going to be a differential equations problem that we're going to work on. So for number 5, it reads, at the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation dW over dt is equal to 1 over 25 times the quantity W minus 300 for the next 20 years. W is measured in tons and T is measured in years from the start of 2010. So for part A, use the tangent line, or use a line tangent to the graph of W at T equals 0 to approximate the amount of solid waste the landfill contains at the end of the first 3 months of 2010. And that would be time is equal to T equal to 1/4. Okay, so what I want you to do now is I want you to pause, okay, and then I want you to work this out yourself. And you may want to do it this way. You work on A, B, and C, or then you work on A, and then watch the video on me answering the question, and then you try to do B and then answer. You can go back and forth, or just do all 3, A, B, and C, and then look at the end how I answered it. Okay, just to check your work. Okay, it's kind of like the homework solutions. Okay, but video style. All right. Okay, so go ahead and pause the video and go ahead and answer it the way you want to. Okay, for part A, first what we have to do to find the tangent line is we need to find the slope and a point, okay? And the point that we're trying to find this at is at T equals 0, okay? So we know from the very first statement that W of 0 is equal to 1,400 tons, okay? And then we also need, we know that dW over dt is equal to 1 over 25 times W minus 300. Okay, so for part A, all right, what we know is we got our point, right? W0 is equal to 1,400. Okay, so we know this W at time t equals 0, we got to find that, right? dW dt at t equals 0. And what we know is that that's equal to 1 over 25 times, and this is the W, not the T, okay? So it'd be 1,400 minus 300, okay? And then that would equal 1 over 25 times, and then this would be 1,100, not 11,000, whoops. 1,100 with the common line spot. So 1,100. And so that would come out to be 44. Okay, so that's our slope. This is our point. That's our slope. We know that our tangent line is going to be y is equal to, okay, 44 times t minus 0, because this happened at t equals 0, plus 1400. Okay, well, t minus 0 is just t. So this is y is equal to 44t plus 1400. Okay, and then the other part they want you to do is to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010, and that would be t equals 1/4. Okay, so we're going to find w of 1/4, and that's approximately 44 times 1/4 plus 1400. So 44 times 1/4, that would be 11. Okay, so this would be 11 plus 1400, and that would be 1411, and that would be in tons. Okay, and that's part A. So go ahead and make the corrections, all right, with a different colored pen, okay, or different colored markers, so I can tell the difference between what you wrote and your corrections, okay? And then pause it, or if you did them all, just go ahead and keep watching, okay? And we'll do part B next. All right, for part B, okay, they're asking you to find the second derivative of W with respect to t for the second time, okay? And we want this in terms of w, so our answer will have w in it, okay? So we knew that dw over dt is equal to 1 over 25 times w minus 300. Okay, you could, if you wanted to, go ahead and take the derivative right now, or I'm going to do this. I'm going to distribute this, so the 1 over 25, so that'd be 1 over 25 w minus, and then 300 divided by 25, which would be 12. Okay. Now, what happens when we take the derivative of this, okay, with respect to t? So this is going to be 0. This is going to be dw dt, okay? So the second derivative of w with respect to time for the second time, okay, that's the notation. It's in the question too, okay? It would be 1 over 25 times, and the derivative of w with respect to t would be dw dt, and then minus 0, okay? Now dw, this is in terms of dw dt. We want in terms of w. Well, we know what dw over dt is. It's this, right? So this becomes 1 over 25 times 1 over 25 times w minus 300, or 1 over, and then 25 times 25 is 625 times w minus 300. Okay, so we want to use this next to determine whether this was, our estimate in part A was an overestimate or an underestimate, right? Okay, and the way to do that is to look at the concavity of it, because we have the tangent line, right? And if we know it's concave up and we have a tangent line that's approximating it, like I'm drawing right here, okay, concave up tangent line, here's the estimate I used for the tangent line, right? And so if it is concave up, then the tangent line estimation would be an underestimate because the actual value is a little bit higher, it's above it, right? Versus if we have a tangent line and we're concave down there, okay, then it would be an overestimate, okay? So we have to determine the concavity at t equals 0, okay? So, and at t equals 0, that's determined by, they have 1,400 tons in the landfill, okay? All right, so we got to find the second derivative of w with respect to t for the second time, and that's equal to 1 over 625 times 1,400 minus 300. Now, 1,400 minus 300, that's going to be 1,100, right? So this is 1 over 625 times 1,100. Now, what do we know about this? We don't really need to calculate it, okay? Because what do we know about this? We know it's greater than 0, right? All right, so the second derivative of w with respect to t for the second time is equal to 1100 over 625, which is greater than 0. So that tells us it's concave up it's concave up here, okay? So since it's concave up, we have this situation, and so our estimation from part A, okay? So our we could write since W of t is concave up, and we know that because the second derivative is positive. Our estimate in part A is an, put a parentheses on the A, is an underestimate. Okay, and that's how you answer part B. Okay, make the corrections, do it in different colored ink or a different colored pencil or something else so I can see the difference, okay? All right, and we'll go to part C now. Okay, so what they're asking you to do is actually to solve and find W of t for part C, okay? So we know, this is a differential equation that we need to solve, okay? So for part C, we know that dW over dt is equal to 1 over 25 times W minus 300. Okay, and we also know that W of 0 is equal to 1400. All right, so this is just simply a separation of variables because we have a product here, right? I can divide both sides by W minus 300 and multiply both sides by dt. So I get 1 over W minus 300 dW is equal to 1 over 25 dt, okay? And so we're gonna integrate both sides. So 1 over W minus 300 dW is equal to the integral of 1 over 25 dt, okay? You could do a u substitution. U would be W minus 300, okay? And then if you take the derivative of u, that'd be du, and it would give you dw, right? Okay, so we really don't need to do the substitution. You can if you want to, it wouldn't be wrong, okay? But really this side right here is just gonna be the natural log of the absolute value of w minus 300, okay? So this becomes the natural log of the absolute value of w minus 300 is equal to 1 over 25 t plus some constant c, okay? All right, so now at this point, you have a couple of options, okay? You can either put in your initial conditions that t is 0 and w is 1400, okay? You could do that, or you could start to solve for w, okay? And for these, when you get the natural log, I like to solve for w first, okay? That's just the way I like to do it, okay? So what I'm gonna do next is I'm gonna exponentiate both sides because I want to get to this w, okay? So I'm going to exponentiate both sides with e, okay? So e to the natural log, or no, not 2, e raised to the natural log of w minus 300 is equal to e to the 1 over 25 t plus c, okay? Now, e to the natural log, they're going to undo each other. We're going to be left with the absolute value of w minus 300 is equal to, and then, all right, so this is exponents, and we're adding, and we do that when we multiply and we have the same base, right? So this is rewritten as e to the 1 over 25t times e to the c. And here's where we did this before is I let this be a whole new constant, okay? So I'm gonna let K, or it doesn't have to be K, it could be A or any other letter. I wouldn't use E or W or T, okay? But you could use any other letter. And then, so I'm gonna call it K, and I'm gonna let K equal E to the C. okay? So the absolute value of W minus 300 is equal to, so this is going to become K, and I'm actually going to put it in first, okay? So I'm going to write it first. So K times e to the 1 over 25 t, okay? All right, so then the next thing you could do is go ahead and put your initial conditions in to get this K value, okay? All right, so W is 1400, so that'd be the absolute value of 1400 minus 300 is equal to K times E to the 1 over 25 times 0, right? So that'd be E to the 0. Well, E to the 0 is just 1. So this is K right here, right? And so we have the absolute value of 14 minus 300. That'd be 1100, right? And we really don't need the absolute value, so it'd just be 1100 is equal to K times E to the 0, and that's 1. And we, guess what? We just found K. K is 1100, okay? Now, what we need to do next is we need to go back and we need to solve this for W. So right here, back at this step right here, okay, I'm gonna put my K back in. So now what I have is, and I'm gonna slide my paper up just a little bit, okay? So what I have is the absolute value of W minus 300 is equal to 1100 E times E raised to the 1 over 25 T, okay? Now, to solve an absolute, now we have to solve this absolute value equation, right? To get W by itself, okay? So what we know is that this could either be positive or negative, okay? So W minus 300 is equivalent to 1,100. Whoops, I forgot. I said plus or minus and then I didn't write it. Okay, so let me wipe this out. Okay, so plus W minus 300 is equal to positive or negative 1,100 E to the 1 over 25 T, okay? And so I'm gonna move the 300 over. So W is equal to 300 plus or minus 1,100 E to the 1 over 25 T, okay? Now, this is actually giving us two answers, right? 300 plus 1100 and 300 minus 1100, okay? So which is it, okay? So we have two choices. We have W is equal to 300 plus 1100 E to the 1 over 25 T, or we have W is equal to 300 minus 1100 E to the 1 over 25 times T. Okay, now which one is it? Well, what do we know? From our very first part, we know that if we put 0 into W, right, we're supposed to get 1400 out. Okay, so what happens when I put 0 in for T here? So that would be W is equal to 300 plus 1100 E to the 1 over 25 times 0. Well, this would be 0. That'd be E to the 0, and E to the 0 would be 1, and that'd be 1100. So this would give us W is equal to 1400. Now over here, it won't. Okay, so W is equal to 300 minus 1100 E to the 1 over 25 times 0, right? And that's going to be 0. That's going to be E to the 0. And E to the 0 is 1. And so 300 minus 1100, that just give you negative 800, which isn't the value that we're supposed to be getting, right? We're supposed to be getting 400 or 1400, right? So guess what? This is not our answer. So I would just cross it out and I would say, okay, so W of T is exactly now, okay, we would say 1100 E to the 1 over 25 T plus 300, okay? And that would be your answer to this problem, okay? Now, you could also write it as 300 plus this. I mean, that's how I wrote it up here. You could do it either way, and it's fine, because that's just a difference of order, okay? All right, and that's your answer, okay? All right. All right, that's the first differential equation. So we're going to spend all week working on two types of problems: differential equations and rates and accumulation, all this week, okay? And then we're going to switch up and we're going to do two different topics next week, okay? All right, and we'll talk more later, okay? All right, you guys, take care.